For today's day in review, you should be able to answer the daily learning objectives. Why is stoichiometry important to chemists? Why is it important to have a balanced chemical equation? And what is that mole-to-mole ratio? We said stoichiometry was the study of quantitative aspects of chemical reactions. Up until now, we pretty much have looked at qualitative aspects, and now we want to actually look at amounts that are produced given certain amounts that were required. Stoichiometry gets linked up a lot with recipes, or specifically baking, because when you're baking something, it's all about ratios, and with stoichiometry, it's also about ratios, and specifically those mole-to-mole ratios. So we had gone over the example about making chocolate chip cookies and looking at the ratios of eggs to sugar to vanilla, and how that ratio is an important part of the recipe. If you don't know the ratio, all you know is you have eggs, sugar, flour, milk, butter. How do you know the order and in what quantities to combine them to make the product? So if we had 6 eggs, we know that we could make 3 batches going off that 2-to-1 ratio. 1 egg would make a half a batch. 3 cups of sugar would give us 3 batches. 1.5 cups of sugar would give us 1.5 batches, and so on. Same thing with the conservation of mass. This is a law that we've looked at over and over again. We said that in a chemical equation, the products must equal in mass and number of the reactants. You can't lose mass in a chemical reaction. It has to be conserved. It has to change form and be accounted for on both sides of that equation. So it's important in chemistry because you don't want to waste stuff. You need to be able to predict how much product you're going to get if you only have a certain amount of reactant. That avoids waste, particularly if something's expensive or something's toxic. You don't want to use too much or produce too little. You want to minimize your waste, maximize your output. So if we were going to buy tires for cars, we need to know the ratio of tires to cars. So everybody knows that that's a 4-to-1 ratio. So in this case, we've got enough tires for 6 cars because of that ratio. But if we only needed enough tires for 2 cars, we would only buy 8 tires. You wouldn't buy 24 tires. That would be a waste. Same thing with chemistry. You need to know the ratio so that you can get the exact amount of product. So here's what we deal with in chemistry. Here we're given a amount of reactant, and we're asked how much product is going to be. So in this case, it's almost like saying we've got 1.5 cups of flour. How much bread can I make? Well, I can't tell you how much bread you can make with 1.5 cups flour. I have to know the recipe first. So just like the eggs and the cookies, the tires and the cars, we have to know the ratio of silver nitrate to silver chloride in order to figure it out. So how do we do it? We have to write the balanced chemical equation. So that's your first step. So we have silver nitrate reacting with sodium chloride to form silver chloride and the missing product, which we would figure out by a double replacement reaction, which is sodium nitrate. So here's our equation. If this were a recipe and it just said flour, eggs, sugar, milk, we would have to know the amounts. We'd have to know how many cups, how many tablespoons. In this case, we're going to have to know how many moles. And the only way we could figure that out is by writing the balanced equation. So once we write the balanced equation, we're going to inspect it to find the molar ratios. In this case, the equation was already balanced, so we're going to look at the coefficients for silver, sodium chloride, silver chloride, and sodium nitrate. So we could see that since there's no coefficient there, that means this is 1, 1, and 1. So our ratios here are 1 to 1 to 1 to 1. And that's something you're going to look at in your homework when you do the reading, looking at those ratios. So this reaction tells us for every 1 mole of silver nitrate, we get 1 mole of silver chloride, but we're not given moles, we're given grams. So that means we have to do a conversion. We have to get out of grams of silver nitrate and we have to get into moles of silver nitrate in order to use this recipe. So let's do that. Let's convert grams into moles. So we were given 17.0 grams of silver nitrate. And we know if we have 1 mole of silver nitrate, and I look at the periodic table and I look at the mass of silver, nitrogen, and 3 oxygens, I see it comes up to 169.9 grams of silver nitrate. Now I'm in moles of silver nitrate. If you do the math, and you could do this in your head, you see that this is really almost 170. If you want to factor out the 17 goes into itself once, it goes into 170 10 times. This tells you you have 1/10 of a mole. But if you don't see that, we're going to continue on with this equation. Now we have to go back to the original equation and compare that mole-to-mole ratio. Remember, this equation said if you had 1 mole of silver nitrate, you were going to get 1 mole of silver chloride. So we need to plug that in. Go back to our equation. We have 17.0 grams of silver nitrate. And we knew that 1 mole of silver nitrate has a molar mass of 169.9 grams. Now, we want to get out of moles of silver nitrate. We want to get into moles of silver chloride. And we're going to do that by plugging in that mole-to-mole ratio. For every 1 mole of silver nitrate we react, we're going to get produced 1 mole of silver chloride. Now, if we stopped here, we'd be in moles of silver chloride. But the question is asking us not for moles of silver chloride, it's asking us for grams. So stopping here, we'd be in moles of silver chloride. We want to convert those moles of silver chloride into grams. So that means we have to take it one more step. So again, our equation, 17.0 grams of silver nitrate, 1 mole of silver nitrate has a mass of 169.9 grams off the periodic table. We know if we react 1 mole of silver nitrate, we get 1 mole of silver chloride. And that's straight off of the balanced equation. Now we want to get out of moles of silver chloride into grams. And I believe that was 149 grams. I'm not sure. So now to do the math. We could see that we can factor out 17 from 170. And so this says we're going to take 149 and divide it by 10. So that gives us 14.9 grams of silver chloride produced. And that's our answer. Oh, it was 143. Sorry about that. So the solving process. We said start with grams given, convert to moles, use that mole-to-mole ratio from your balanced chemical equation. That's why it's important to balance it, because you have to get that mole-to-mole ratio. Then you're going to convert those moles into grams, and you'll end with the grams required or produced. And I showed you the little map. Start with grams given, convert to moles, mole-to-mole ratio, Convert those moles to grams, and you're going to end with grams produced or required. So the example we did in class was figuring out how many grams of hydrogen were produced from 11.5 grams of sodium when it reacted with water. So start with grams given according to our solving process, and that's 11.5 grams of sodium. Convert that into moles. 1 mole of sodium has a mass of 23 grams off the periodic table. Then we need to go into the mole-to-mole ratio. So in order to get to the mole-to-mole ratio, we have to look at that balanced equation. So we are going to react sodium with water, and we're going to get sodium hydroxide and hydrogen gas. Now we have to balance this equation in order to get the ratio that needs to go here. So let's balance this out. We've got 3 hydrogens on the right, 2 on the left, so I'm going to make that odd number even by doubling the odd. Now I have 4 hydrogens on the left, 4 on the right, 2 on the left, so I'm going to put 2 in front of the H2O to double up those hydrogens. So now it looks like the oxygen count is good. I need to add 2 sodiums. Now we're balanced. Now what I would suggest you do is underline the coefficients of what you're being asked for. So we're given grams of sodium, and we want to know about grams of hydrogen. So these are the coefficients that we're going to be dealing with in our mole-to-mole ratio. Sodium and hydrogen. So that's what's going to go here in that part of the equation. Yikes, didn't mean to do that. Okay, so now we're going to put these coefficients in this area for our mole-to-mole ratio. So this says for every 2 moles of sodium, we are going to produce 1 mole of hydrogen. Now if we stopped here, we'd be in moles of hydrogen, but the question is asking us for grams. So now we need to take it one more step, and we're going to get out of moles of hydrogen into grams. So I know if I have 1 mole of hydrogen off the periodic table, remember this is a diatomic molecule, so this is saying H plus H. So it's going to be 2 grams, not 1. It's going to be 2 grams. Okay, now let's see what we can factor out of this. We can get rid of this 2 and this 2, because 2 divided by 2 is 1. And now we're going to look at 11.5. How many times can 11.5 go into 23? It can go into 23 twice. It goes into itself once. So our answer here is 1 divided by 2, or 0.5. So you have 0.5 grams of hydrogen produced. And that's your answer. Let's look at one more. More practice. How many grams of water are produced when 32 grams of methane are combusted with excess oxygen? So we have to put our recipe out there first. So remember, find out what goes on the left and what goes on the right. We've got methane being combusted, so that means we're going to react methane with oxygen. Products of combustion are carbon dioxide and water. So this needs to be balanced because right now it just says eggs, flour, milk. We need to know the ratio. What ratio will they combine in? So we're going to balance this. So let's look at the hydrogen count on the left is 4. On the right it's 2. So I see I need two water molecules. The oxygen count on the right now is 4, and it's only 2 on the left, so I need 2 oxygen molecules. Now we're going to underline the coefficients that we're interested in because we're going to need those for that mole-to-mole ratio. So we're asked about methane, and we're asked about water. So our mole ratio here is 1 to 2. So when we get to that point in the equation, that's what we're going to plug in. So now we're going to start with grams given and convert it into moles. And we were given 32 grams of methane. If I have 1 mole of methane, off the periodic table, it's carbon plus four hydrogens. It comes out to be 16 grams of methane. So if you see this now, you could see 32 divided by 16. That's going to give us a half of a mole. So if we had 1 mole, according to this equation, we would get 2 moles of water. If we have a half of a mole, oh, I'm sorry, we actually have 2 moles. 32 divided by 16 gives us 2. If we have 1 mole of methane, we're going to get 2 moles of water. Since we have 2 moles of methane, that should give us 4 moles of water, and then you can convert that to grams. If you don't see that, we can just put it into the mole-mole ratio machine. Okay, so now this is the part where we take those coefficients and we plug it in here. So for every 1 mole, from here, 1 mole of methane, we'll get 2 moles of water. Now we're going to get out of moles of water into grams. And I know if I have 1 mole of water, it has a molar mass of 18 grams. That's hydrogen plus the oxygen. Okay, let's see what we can factor out now to make our lives a little bit easier. We know that 32 divided by 16, 16 goes into itself once. It'll go into 32 twice. So this is saying 2 times 2 times 18. So 2 times 2 is 4, and 18 times 4 is 73. So our answer is 73 grams of water produced. Okay, so we have to write our balanced chemical equation here. We've got methane. Oh, we already did this one. Sorry, guys. Next one. I want you to try this next one on your own. Pause the recording and then come back to it and check your answer. Okay, here's the equation again. In this case, we're looking at the methane to carbon dioxide ratio, which we put in here. So once we set this up, let's factor out what we can. I see 22 and 44. 22 goes into itself once, 44 twice. So this means we have 16 divided by 2, which is going to give us 8.0 grams of methane reacted. Hope you got that.